Okay, so this problem gives us an idea of what is a gradient. Okay, like not mathematically, but a bit of geometrically, what is a gradient. So as you can see, let us take this two-dimensional function. Okay, let us take this two-dimensional function. And as you can see, it's a x square plus 2y square minus 2xy minus 2x equals to 7. So if you plot it, you will get a curve like this. I ask you to do it in Desmos for a quick one. Okay. So, and we will play with this curve a lot in gradient descent also. So this curve is our gradient descent. We will learn gradient descent using this function. Okay, so I want you to visualize this curve in Python or in Desmos. You have both options. So then what I did is, I know that minus 1, 1 will pass, is a point on the curve. So minus 1 means here, 1 means here. So somewhere here, we'll have our point, okay? Okay, so at this point, we are trying to evaluate the slope. So what is the slope? Slope is dy by dx. You already. So we are interested in evaluating the slope at minus 1, 1. So what is dy by dx at minus 1, 1? Okay, so as you can see, I have differentiated the function. 7 won't come, it's a constant. Here you have to apply product rule, 2xy. And that's the mistake we had done last class. We missed one term. Okay, so careful. So this is your new term now. This is your new equation. From there, you can make dy by dx the subject and put everything on the right hand side and do the computation. So in that way, you get dy by dx as this quantity. Okay. So now you can put minus 1, 1 to evaluate the slope at minus 1, 1. So if you put minus 1, 1 here, you are getting the slope equal to 1. If the slope is positive, that means it makes an acute angle with the x-axis. Okay, if slope is positive, it makes an acute angle with the x-axis. Why is that? Because slope is tan theta, the theta angle made by the x-axis. Okay, and tan theta is positive for your acute angles. So therefore, this is theta, and tan theta equals to 1 means theta equals to 45 degrees. Okay, so that means like you will make a 45-degree line with this. All right. Okay, so yeah, so now I'm computing the gradient. Okay, so can you compute the gradient here? I have computed it here. It's dou f by dou x, dou f by dou y transpose. So it's a column, it's just a vector, column vector. Okay, dou f by dou x we can do. Treat only x as variable, keeping y constant. Then you will get dou f by dou x. Dou f by dou y, you're differentiating partially with respect to y. That means keep x to be constant and differentiate with respect to y. Okay, so you will get these two quantities. Now, can we evaluate gradient at the point minus 1, 1? What you will get? Can anyone tell me? Is it minus 6, 6? Minus 6, 6 you will get. Minus 6, 6 means where it will lie? So minus 1, 1 is here. So similarly, it will be scaled 6 times, isn't it? Minus 6, 6. So it will be a line. Select my black page. Okay, so yes, so minus 6, 6 will lie somewhere here, isn't it? A black dot. But main reason is this vector will pass through origin. Okay, this vector will pass through origin like this, and the direction is this. Okay, note that. Do you see an interpretation, a geometrical interpretation to this? This normal line is perpendicular to your slope, to your tangent line, isn't it? Yes. So gradient is perpendicular to your normal. Gradient is perpendicular to your normal. Okay, that's the gradient is perpendicular to your tangent. Okay, so if you compute gradient vector, you will get your normal direction. All right, so this is the motivation, like where the gradient direction is, it's perpendicular to the tangent. All right, So this is the gradient and their importance before learning gradient descent algorithm. Okay. So if someone asks you, can you give me a direction to the normal to the curve? Then what we shall do? If it's a two-dimensional curve and someone asks you, give me a normal direction to the curve. So without any hesitation, you will just compute the gradient. Okay, just compute the gradient and this vector will give you the direction of the normal vector to the curve. So see that it is normal to the curve and also to the tangent. Okay, all right. So yeah, then we will see another example based on this problem also. Also, can everyone open Desmos? Everyone open Desmos? So what curve I will write? Can you please, what I say, do that? Yes. So we will do this here. Okay. So everyone open to your Desmos? So we will consider three curves. Okay. So fxy equals to x square plus 2y square minus 2xy, very similar curve as last, same as last. This is one curve. Another curve is g of x comma y equals to x square plus 2y square minus 2xy minus 2x equals to 27. All right. H of x comma y equals to x square plus 2y square minus 2xy minus 2x equals to 63. Your job is to plot these three functions f, g, and h in Desmos. Okay, and confirm that you are indeed getting these curves. What is actually happening here? So if we take a small constant, that is the center curve f. If I take a bigger constant 27, that is the middle one. If I take 63, you will get more bigger. So the more right hand side value you increase, your what you call the level curve increases, okay, in size. And okay, so that is confirmed for you. Okay. Now we will see an importance of the gradient here. Okay. So can you confirm me that, see, previously we found gradient of f at -1, 1 and an expression we found for the gradient. Okay, what expression we found? Gradient 2x minus 2y minus 2 and 4y minus 2x. Now, can you appreciate that the same gradient you will get for g and h? Why am I saying that? Because the function is totally the same and only differs in the constant sign, constant value, and that constant value turns out to be 0 when you are differentiating it. So therefore, gradient of f is the same as gradient of g is the same as gradient of h. What does it mean? It means that if the gradient is same, they will share the same normal vector. Okay, what does it mean? Like if you find like we found that -1, 1 was here and we did a tangent and perpendicular to that was the direction of the gradient. Okay, but now we are saying that gradient of f, gradient of g, gradient of h are the same. That means all will be having this direction. This curve will have this gradient direction. This g curve will also have that gradient direction. H curve will also have the same gradient direction. Okay with you till now? All right. So this is a good point to see that f of x comma y, g of x comma y, and h of x comma y share the same normal. All right. Now, can you like tell me like one thing? If you want to shift from function f to function g, if you want to shift from function f to function g, then what is your shortest path in doing that? There are many paths actually. There are many paths like this can be from here, you can go till here, you can go till here. Okay, from here also you can approach. So which one is the shortest path? The perpendicular one. The normal direction is the shortest path. So therefore the gradient will also give you a direction where you can you can jump from one function to another function in a shortest time possible. Okay, through the shortest path. So that's one of the observation we have. Okay, all right. And one more thing have you observed here from this simple example is, like, if the value of this curve x square plus 2y square minus 2xy minus 2x, the value of this curve increases in the direction of gradient. Can you understand it? See, as you move here, 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 more towards outside, your value of the function increases. Okay, and that's the direction of the gradient. Okay, so if you want to see where your function is actually increasing, okay, so you have to see the direction of the gradient. Okay, what does it mean in a converse way? If your function is increasing in the direction of gradient, it also means the value of this function, okay, decreases at the slowest rate in minus grad f direction. Okay with you? Any issues? Yeah. So what did we get? So the value of the function, the value of x square plus 2y square minus this function increases, okay, at the fastest rate in which direction? In which direction? Hmm? In which direction this column? So the value of x square plus 2y square minus 2xy, this function increases at the fastest rate in which direction? This is one of the simplest examples to understand gradient. Okay, it can't be any simpler than this. So they just apply your common sense. F has the value 7, G has the value 27, H has the value 63. And your gradient direction is this side. So the value of this increases at the fastest rate in which direction? Which direction? So then if I say the value of the same decreases, okay, at a slowest rate, in which direction? The value of the same function decreases at a slowest rate. In which direction? If in one direction it is increasing very fast, if you go opposite direction, it will slow. Okay, think of it as a hill. Okay, this is the hill. You have a bike and you are trying to go here. Okay, it will be very slow. But the moment you come from this side, it is very fast. The same concept. So in minus of that direction. So therefore, understanding this concept was most important. So if you want your function to increase at a fastest rate, you have to go in grad f direction, that is gradient direction. Okay. If you want your function to decrease at a slowest rate, I have taken a negation of this statement, then it will be minus grad f direction. Okay. So these things you have to learn. These things here is your only way to know about gradient descent algorithm. Okay. Okay, cool. Yeah. All right. So this motivates me. Another motivation I can give it to you is here. Okay. So this is an example of the mountain. All right. So this is this is an example of the mountain. Okay. So you can see we have to reach here. We have to reach here. Jokes apart, just learn, then you can learn. So we have to go from here. So you can see people are traveling here. Okay. This direction people are traveling. All right. So your job is to travel from here to this point. This is your destination. This is your destination. Okay. This is your destination D. Okay. So you have to travel from this to here or different areas, up to you. But which path you have to take such that you can reach to this valley or to this lake at a less time, at the lowest time possible. So that's the question. So this motivates, like you can see, some people are walking in this direction, but I walked in this direction. This bunch of people were walking in this, but I walked in this direction. Okay. So the idea is how you will go from the top of the hill to the bottom of the lake. Okay. This is your target. You can see a lot of people are like, they stand here and they see all these things. This is the Tongariro crossing lake. And here, this water is not simple. Here you will get these fumes coming out due to sulfur. Okay. So you are not allowed to bath also here. But being there is good for your health because of sulfur and all. So the gas and all those things nearby that lake is quite good. So if you know about Indian valleys also, let me know. I tried to find a good photo, but this is the photo I could. Okay. Yeah. So tell me, like, yeah, this was during my PhD. So after I defended my PhD, I thought I should go a bit outside of my computational environment and enjoy the surroundings. So I decided to go here. Okay. So still not many change. I still bring the same bag to this. So anyway, so this is one of the motivation for you. So instead of this function, instead of a 3D function, think of this as a 3D function. The mountains and all are like 3D functions. Okay, because they have a height, and through that step you have to come to the bottom of the lake. Okay. So yeah. So this motivates me to the gradient descent concept. Gradient descent will ask you the same, like from a given function, which direction you have to take in a 3D or 2D function so as to reach to the desired minimum or desired maximum. Okay. So this is what a motivation I am trying to give. Okay. So we'll start with the algorithm. Okay. So what is gradient descent? We already heard about this method, but what is this gradient descent method? Okay. Why the term gradient is used? Finally, it is an optimization algorithm. Okay. So this is a method which uses gradient information. Like you have to compute gradient. In that way, you are getting the gradient information for one purpose, for optimization. Okay. So this is an optimization algorithm where you use the information of gradient. Okay. So here, suppose you can always do the negation. So we will take either minimum or maximum of a function. So here we will take minimum, and if you take minus of that, it will be minimum of fx is maximum of minus fx. So therefore, our job is to find x star vector, which is this. You already know about this. So it will scan through all the x input vectors evaluated at your function f, and it will take the minimum of that value. Okay, that's like at which value that minimum is attained. Minimum of f is attained, and that is stored as x star vector. Okay. Starting onwards, we are thinking that we are in an dimensional space. Okay. So therefore, this is a multidimensional optimization. Okay. And this method needs a starting initial guess. Okay. Say our starting initial guess. Our starting initial guess is as usual x naught vector. Okay, x0. So further things we can call it x1, x2, x3, and so on. Okay. So what we do? So this is the algorithm. So here I want to bring you back to this problem again. So here what you are doing? Here basically what you are doing. So here you are thinking that you start from here and maybe go in this way, or maybe start from here, go in this way. So there are many options. What brings us those options? Direction. Direction gives us many options. This is one direction. This is another direction. Okay, this is another direction. So direction, which direction shall we go in order to minimize our function? So therefore, in optimization problem, which direction shall we go is a parameter. Okay, like in numerical methods, you already learned about root finding last semester. Step size was a parameter. Okay, each step size how you will go so as to reach to the destination. Now you are asking how much step size I have to go to reach to the destination, and also which direction I have to go. Which direction I have to go to reach to the minimal point. Okay, so therefore here, even though there are a lot of directions, so direction is one of your parameter in gradient descent algorithm. Okay, so therefore, without any delay, I will write the iteration. K plus 1 will obviously depend on the kth iteration. That's for every numerical method. The future iterate will depend on the past iterate. So xk plus 1 definitely depends on xk, fine. But which direction shall we go and how much step size we have to go? That is the important thing. How we will incorporate that in this. Now what we need? We have our initial point xk where I'm standing. Now I have to decide whether I have to go this way or straight, and how much quantity I have to go. One step at a time or two step at a time. You understood? So there are two quantities here. So therefore, see, motivated, we will introduce two more. HK and DK. Okay, what is HK? HK will be your step size, and DK will be your descent direction. Okay, descent direction, or in other words, it's also known as search direction. Because you don't know, in this method, you don't know which direction you have to go. Maybe this direction, shortest path. Maybe we don't know. So we have to collect data. You have to collect real-time data and find which direction you can go, which will give you a like steepest direction so that you can reach faster to this lake. This is a competition actually, because there are a lot of people, okay, and you have to reach there first in order to enjoy it more. Okay, so reaching here is a goal. How fast you can reach from others. Okay, all right. So you already know now this is the gradient descent first algorithm we are seeing. It's an iterative equation. So you can see every time now it will decide a direction, it will decide a step size, and it will iterate your equation, go back to the next step, xk plus 1. Okay. All right. But only this is sufficient. Is only doing this iterative equation sufficient? Do you think? Or we need some more algorithms, some more conditions? See, this is our problem. X star equals to, we are finding minimum of that function f. Okay. X is a vector here. That means f is a function of more than one variable. Okay. And we are starting from initial guess x0. And I am saying that this is our iterative equation. We have to proceed so as to reach the minimum of the function. Okay. Now my question is this enough? Is this enough, or do we need to have, see, we can't believe this equation. How can we believe this equation? That's my question. But if we have one more condition, we can definitely believe this equation. How can we know that the direction we are going at xk plus 1 is actually towards the minimum direction? It might be towards some other direction which is not at the minimum also. Isn't it? That's also a possibility. Isn't it? So how? So what we have to do? So we have to put an extra condition such that this is your iterative equation, fine, but we have to put a condition such that f evaluated at xk plus 1 should be less than f evaluated at xk direction. Yes, is that clear? If that is the case, then you can expect that yes, every time my function value is decreasing, and then it's a positive hope that I will reach towards the minimum of my function. Good. So far good. So far good. Okay. So there is one more thing, like our descent direction. Our descent direction. So think about the function is getting converging. Okay. That means you are iterating. If it reaches a minimum to the function, okay, what will happen? This x and this x will be very similar, right? Xk plus 1 and xk will be very similar if they are converging towards the minimum. Then what does it mean? Hk dk will be very close to 0. Now hk can't be 0 because it's your step size. Now dk has to be 0. What does it mean to a direction to be 0? So therefore you have to take the norm of the direction. So when I am saying this is a vector v, what does it mean? In your class 12th, you know, a vector means it has a starting point and an ending point. And it has a magnitude. What does a vector have? Vector has a magnitude and a direction. That is what is a vector. So that is what is a vector. So therefore, dk is a vector. So it doesn't only have direction, it also has a magnitude. Okay. So how you will get that magnitude? You have to take the norm. So norm of dk less than epsilon. Norm of dk less than epsilon means your method is converging to a minimum. Okay, that will be our stopping criteria, which we will also use in our code. Okay. All right. Now the question is, okay, you gave this condition, but then even if you give this condition, there will be a lot of different directions. Still, there will be a lot of different directions. So the question is, the most important part of gradient descent is how well you will choose your, how well can you choose your direction D. Okay, so to do that, we have to like expand using Taylor series. Okay. How you will have to expand? See, in any numerical method we discussed in this semester, to develop a method, we always use Taylor series expansion. May it be differentiation, may it be ODE, okay, may it be PDE. Optimization, everywhere we have expanded using Taylor series. That's the best part of anything. Okay. Yeah. So to select a good D, we expand first of all fxk plus 1. So how can we expand this in Taylor series? Can you tell me? Of course, if you are defining using Taylor series, the first term, what is xk plus 1? Xk plus 1 is xk plus hk dk. You know now, fx plus h. You should get a intuition that this is of the form f of x plus h. Then you know it is f of x plus h of f prime of x plus h square by 2 f double prime of x, so on. But can you use that here? No. Why? Because f is not a single variable function. F is having a vector valued function, x bar. It depends on more than one variable. Therefore, instead of differentiation, gradient will come into picture. There is no harm. Whenever you are seeing differentiation, just replace it with gradient. It's done, nothing else. Okay, so how shall we, can anyone tell me what's the, so we have to expand through multivariable Taylor expansion. multivariable Taylor expansion. Okay. How can we write this? This will be another important point we will be coming through. Very important. Okay. So just see, you can write this as f of xk. This is usual, you already know it. Obviously, this term will be there. Then from the Taylor series expansion, there will be this quantity. Okay. Don't have to think this is hard. It just follows your normal Taylor series expansion. Here you would have taken d by dx. Instead of d by dx, I just took gradient. And then you will obviously have a higher order term of hk square. Now, can we do something new? Can we do something new? Can we take this guy to here? The left. If we take that guy to the left, what we will get? Change in function, isn't it? Change in function at xk plus 1, f of xk plus 1 minus f of xk. What does it mean? Change of function in the iteration, isn't it? Yes. So I can write it as delta f. Delta f, change in function at one iteration, from kth iteration to k plus 1th iteration. Yes. And what is that quantity? This is not equal to. It would write equal to, I should write approximately, because I'm not taking this higher order term. But it is there. I'm neglecting it. So I can't put equal to sign. I can approximate. Okay. What should it be? Hk dk transpose gradient of f at xk. So far clear? So far? Now this is a bit of mathematical notation. Okay. This guy, this. So remember that dk transpose is a vector. Dk transpose is not a scalar. Hk is a scalar. Step size is a scalar. But dk transpose is a vector. Gradient of f is also a vector. How are we multiplying vectors? And finally is the change of function, which is a value. So left side is a value. This side should also be a value, no? This side can't be a vector, right? In order to match, value can't be equal to a vector. So this is a value, but these are vectors. So therefore, there is a very important term which I have missed. Okay, what is that? You have to take a dot product. Okay, dot product of these two vectors. Dk transpose gradient of f at xk. Okay. So far it's okay, or so this is known as, I urge you to search in Wikipedia. This is the directional derivative in multi dimensions. Okay. So this is directional derivative. Directional derivative in direction of which direction? Dk. Please Google this directional derivative and you will get a lot of different expression for directional derivative, and one of them will be something vector multiplied by gradient. Okay. In other cases, in your one-dimensional case, you will have some vector dot product of some d by dx. Okay, then it will be a one dimension. So that's a directional derivative in one dimension. Here it's a directional derivative in n dimensions because we are having this gradient. So whatever formulas, don't need to get afraid. D by dx, it's one dimension. The analog is gradient of f in n dimensions. So whichever formula you are using, d by dx, just replace with gradient. Okay. Okay, so far. Now think about what we want. We want to minimize f. We want to minimize f. You only told me that we need this quantity, right? f of xk plus 1 should be less than f of xk if you want your function get minimized. If this is the case, then what should be delta f? F xk plus 1 minus f of xk. Negative, less than 0. How many of you did not understand this? F of xk plus 1 is less than f of xk, isn't it? Then what is f of xk plus 1 minus f of xk? Just take this quantity onto the left, less than 0. Have you seen that quantity somewhere? Yes, where? Delta f. We took this quantity there. Clear? So, in order to have our minimization function, f, in order to have f to be minimum, we need delta f less than 0. Isn't it? What is delta f? F of xk plus 1 minus f of xk less than 0. Isn't it? Understood? Understood. So what is that quantity delta f? This quantity hk dk transpose dot grad f. So can we put that less than 0? Can h be less than 0? So what we have to have? So what does this mean? This means hk dk transpose dot product with gradient of f at xk time step is less than 0. Now h is your step size, which is a positive quantity. It can't be non-zero. It can't be negative. Okay, so this can't be negative. So this implies dk transpose dot gradient of f at xk should be less than 0, isn't it? If you want your function to attain the minimum, if you want to find minimum, then this condition should get satisfied. Okay, now you can see how we are building up the theory. Okay, for f to have a minimum function using gradient descent. Okay, all right. So what does this mean? What does this dot product mean? Can we take the dot product now? If we take dot product now, what we will have? Norm of dk transpose, isn't it? Norm of grad f at xk times the cos theta less than 0. Good so far? So far, so good. Any issues with this now? What is a bar dot b bar? Dot product of two vectors. Here we could have taken just absolute value, but here we are taking norm because it's a vector. Okay, n dimensional. And cos theta. Theta is the angle between A and B. A is here, B is here, this is theta. So far good. So this guy will be positive, this guy will be positive. So the negative is due to the cos theta. This means cos theta should be less than 0. Cos theta should be less than 0. Okay. Now, one idea. Cos theta should be less than 0. But when is cos theta minimum? We can do the best, isn't it? You can get cos theta minus 0.5, fine. But why need to take minus 0.5 if you can get to minus 1? Minus 1 is the maximum value of cos, isn't it? Minimum value of cos. And maximum is 1. So cos theta is less than 0. So you have the here. So how much theta you will set? This way. The cos theta is less than 0, so we want to minimize cos theta. When at what value of theta cos theta is minimum? So theta equals to pi. Okay, for theta equals to pi, we have cos theta equals to minimum, that is minus 1. So therefore, in steepest descent method, okay, in steepest descent method, Okay, we need to have the angle between. So what is this theta? What is this theta? This theta is the angle between dk and grad fk, isn't it? Yes, and that is equal to pi. So that means dk direction of your search and your gradient direction are totally opposite to each other. Okay, so and the rate of minimization is highest in this direction. So the rate of minimization highest in this direction. All right. So rate of minimization, what is rate of minimization actually means? So this rate of minimization refers to the reduction in the value of the function over unit distance. Okay. So just get hold of this name, nothing to worry about it. Okay, now we know which direction shall we go. It should be opposite to the direction of the gradient. dk is opposite to gradient. That's why the angle is pi. So direction part we solved. Now there is one more part. You know, I started with this equation. I started with this equation. We solved this part now, dk, which is the search direction. Now this part is there, the step size. Shall we take a constant step size? Or shall we vary the step size according to our iteration? That is one of the issue. That's what we will see using coding. Okay. So what we should do is a straightforward method that comes to mind is in every iteration of this xk plus 1 is xk plus hkd. At every iteration, you find the search direction. Okay. You set the step size and you compute it again and again. So every step you are finding the step size. Okay. That is therefore I have made hk. But this is where the algorithm is getting slow. Okay. At every step, if you find the best step size, then obviously your algorithm will be slow. Else, so what is the remedy? Maybe we can take constant step size. Constant step size means you don't have to change the step size again and again. Rather, keep the step size constant for throughout the iteration. So we will see both of the cases. Okay. Yeah. So now, since we talked about bit about direction, we will talk a bit about the step size. There are two parameters, step size and the direction. So this HK step size can be obtained from any line search technique. Okay, you will soon see what I'm talking about. So take this example, f of xk plus 1. What is f of xk plus 1? F of xk plus hk dk. Yes. Now this you already know. This you already know. So it is only variable is hk. So this can be thought of as a function phi depending only on hk, isn't it? Or I could have written f of hk also, but I'm just saying that it is depending on only hk step size. Now, can you like, if I frame the problem as like this, find the optimum value of step size h, which minimizes the function f. Then can you appreciate that this is a one-dimensional unconstrained optimization problem? Can you think? Because it only depends on hk. It only depends on hk. It doesn't depend on more than one variable, right? So it's a 1D optimization problem. So finding that optimized h value for which f is minimum is just saying that minimize phi. Minimize phi, isn't it? Is that okay with you? See, f of xk plus 1 is this. That is like phi of hk. F of xk plus 1 should be minimum, right? So it is indirectly saying phi should be minimum. Phi should be minimum given that hk is the variable. Are you still getting? So minimize phi, or that is the function, okay, for which h, okay. That is our job to find, and this is done by one-dimensional optimization problem, isn't it? So Newton-Raphson method, whatever you have learned in 1D optimization solving techniques, you can apply here. Okay. But if you do this, you understood this concept, right? Every iteration, xk plus 1, this I have to do. And again, in that iteration, I have to find what is that optimum value of h. Every iteration, I have to find optimum value of h. Obviously, this is computational expensive, isn't it? At every iteration, if I find this step size, it's going to cost me time. So therefore, the minimization of this function, like finding that h value such that phi is minimum. The minimization of phi h, okay, is at every iteration, the minimization of phi h at every iteration is computationally expensive. Okay. That we will see now. So fully minimization we can't do. Okay, full minimization we can't do. So this is like a full minimization, like fully minimize your work. You try to find that value of phi h. Okay, find h where phi h is minimum. Okay, but instead of, maybe scientists thought, maybe instead of fully minimizing phi h, maybe partially we can minimize phi h. Partially. Okay, you will learn what I meant by partial soon. Okay, that's what brings us to another condition known as the Armijo condition. Okay? This you will encounter quite often in your machine learning course, maybe when optimization will come. This Armijo condition is very important. So Armijo suggested that instead of minimizing phi h at every iteration, maybe we can partially minimize phi h. Okay, or maybe we can take constant step size and get rid of it. Okay, so we will see via coding and see how many iterations does it take to reach for the same function minimum, to the minimum value. Okay, then we'll see which method is better, isn't it? All right, so before that, I think I should give you a problem to solve. Okay, till now you understood the role of h, isn't it? You understood the role of direction dk and the role of step size. Okay, so before moving to the deep into the role of step size, maybe we can appreciate a role of direction now. Okay, let us do a direction problem for now. So yes, yeah. So you know you have to do delta f less than 0, isn't it? From the first half of the lecture, delta f is less than 0. How many of you know about it? Delta f is less than 0. So what is delta f less than 0 mean? Hmm? Equal to dot product. D delta f less than 0, that means the further iteration of the map is less than the current iteration of the map. It happens if delta f is less than 0. And what is delta f? Delta f is this quantity we already saw. It is the dot product of dk transpose with the gradient of f, isn't it? Now we will solve a problem based on this. Suppose you have the same example as before. So we will take our favorite function, x square plus 2y square minus 2xy minus 2x. Okay. All right. So can you find gradient? Can you find gradient of f? Gradient of f is what? Direction. So yeah. So f minus 1 comma 1 is 7. Okay. Suppose for dk is our descent direction. Then if it is a minimum descent direction, it has to satisfy dk transpose grad f at xk less than 0, which we discussed here. Okay. Now, can we say like say d equals to say, maybe I'll go to another slide. Say dk equals to d1 d2 transpose. Okay, it's a column vector of d1 d2, right? It's a two vector. Fine with this. Now, can you substitute this value? Can you find dk transpose grad f at xk? That means, yes, like d1 d2 times, what is grad f? Grad f is minus 6,6. So what should we get? Minus 6d1 plus 6d2. Isn't it? Good so far? Huh? Corresponding entries you just have to multiply and add. That's the dot product. Okay. Now, this quantity you told me it should be less than 0 for minimization, right? Is it fine? What does it mean? Can I write this as 6d2 minus d1 is less than 0? What does it mean? d2 is less than d1. Isn't it? So those directions decay with this quantity d1 d2 transpose such that d2 is less than d1 are valid directions of search, problem for the minimum. So this is our interpretation, isn't it? So now you see any d1 d2 you can't take. Can you take 5 1 or 5 10? Can you take 5 10 as your descent direction? Can you take this vector as your descent direction to minimize this function value? Why? Because d2 is not less than d1. Now, can you take d bar equals to say 10 5? Yes. Why? Because d2 is less than d1. So this is a valid step direction, but this is not a valid step direction. You understood why? So now we have a condition on our direction where to go. So this is the advantage of this criterion, the dk transpose grad f xk less than 0. And this helps us to find the direction at which our function will be minimum. Clear? Is it clear? So okay. So here in this slide, we talked about the importance of direction. Slide we talked about importance of direction. Okay. After the distance direction, after the direction search, okay, we will see a direct problem. You already know what is the iterative function for gradient descent, okay, and what is how we can find a good direction, and what is the problem with the step size. Okay, shall we keep it constant? Shall we update the step size at every iteration, which is computationally expensive? Or if we will not do that, shall we partially minimize the step size? Okay, these three options we have, and three options we will check via code which one is the best. Okay. Okay, these three methods are variants of gradient descent. Okay. Anyway, so let us come to the same problem again. Minimize f of x comma y, where is this function x square plus 2y square minus 2xy minus 2x. Okay, this is your function x comma y, which you already saw. Suppose I told you we need an initial direction, isn't it? We need a initial vector x to start for gradient descent. This x vector is say minus 1 comma 1 transpose. Okay, and normal x vector, you can say we can have this x comma 1 just to, yeah. We already did this example via Sylvester criterion, and we found the minimum value of f. Minimum of f equals to 2. Okay, at minus 2 comma 1, is it? At 2 comma 1. At 2 comma 1. So now we will see via gradient descent how it is achieved. Okay. All right. So what shall we do now? So we will take the steepest descent, that is d naught equals to minus of xk or x0. Okay, what is that quantity? What is the quantity? You already found grad f, and we have to put a minus sign. Minus 6 of minus 1 comma 1 transpose. Oh, minimum value of f. Okay, thanks. So minimum value of f is minus 2 at 2 comma 1. We already checked via Sylvester criterion. Okay. Now again, why we are doing this via gradient descent? Just to check whether it is more efficient. Okay. But gradient descent is an algorithm which can work for you in more than 2 dimensions, like 3 or 4. But Sylvester criterion can't work in more than 2. It can work only for 2 dimensions. Okay. So can you find xk plus 1 using this? Xk plus 1 equals to, we know via gradient descent, xk plus hk dk. So this should be x1. We already know x0. So this should be x0 plus h0 d0, isn't it? So x0 we already know. What is it? Minus 1 comma 1. h0. What we should take h0? Maybe h0 we will not decide now. That's what we saw. h0 we will not fix. We will find what h will minimize the function. It's clear, right? We will see now. Okay. h0 you keep it like that. H. Okay. d0 is 6 comma minus 6. So this should be. Is it correct if I write like this? Is it correct if I write like this? Is it correct? Correct. Okay. So now remember this quantity. Remember this quantity. See, direction we found. Direction d naught you found, isn't it? Now what more you have to find? Step size. We have an option of putting a random step size, but we will see that it is not that efficient. Okay. Suppose we are updating the step size at every iteration such that the phi is minimum. Find a step size h such that the phi function is minimum. Okay. So therefore we have to find the phi function, right? Can we compute the phi function for our case? Can you do that? Tell me by doing the calculation. So what you have to do? What you have to do? You have to do. See. Okay, so what shall we do now? See, our h is the problem here, okay? So we have to minimize phi of h. Minimize phi of h. That's our goal, okay? So what is phi of h? Phi of h we already saw, it is x naught plus h naught d naught, isn't it? From this formula. From this formula. Yes, you got it right. So now I ask you to find this phi of h. Then you can find the extremum, isn't it? Because it's a one-dimensional problem. Set the derivative to be 0. You will get a h value that we will take for iteration. Can you put this value and tell me what you get? This is f of x naught. What is x naught? It is x naught. Everything is given now. H naught and d naught, you already have it here. Minus 6 minus 1 comma 1. Can you evaluate this quantity? You already know what is f. Got it. For some time. Okay. So if you set this equal to 0, the derivative, you will get the optimum value of h for which I h is minimum or f is minimum. F is not minimum. F at that iteration is minimum. Okay, that's our idea, right? Minimize f at every iteration so that we will, that's how it finds the direction. You will see the coding. You will see how well this algorithm works. In arbitrary random initial condition, it will find where the minimization is by taking some very curvy path. So just have to understand one iteration. Other iteration you again have to apply again and again. So far it is okay, is it? Can you tell what is the h value here? So let me continue with my h naught only, else it will be confusing to you. So what is h naught you will get? H naught we are getting is 0.2. Yes. Okay. So this should be the step size, h naught equal to 0.2. Where you will put in? Here, because we did not know h naught. Therefore, we found h naught, right? We found h naught, and where we will put to find x1? This one was, sorry. This one was already known to you. D naught was already known, x naught already known, h naught was not known to you. And we found h naught. So can we find x1 now? You just put h value which you got here. So x1 equals to 1 minus 6h minus 1 comma 1 from here, from this equation. Okay. Can you put minus 0.2 and give me the answer? I think you will get this quantity 0.2 minus 0.2. Okay. So this is your next iteration, right? Okay. Everyone happy with this first iteration, how we did in gradient descent? See, I will reiterate what we did so far so that you can catch up. We told minimize f of xy this, where our starting vector is this. Gradient descent always needs an initial condition to start with. So we took this minus 1 comma 1 transpose. You can take other also. Okay. Then what we took, d naught is minus of grad this. From minimization condition, we knew this quantity. So we found d naught equals to minus 6 of this quantity. Okay. This is the direction we found. What else we need to find? We know this direction. H naught we don't. That we have to find h naught. We can take step size, but I'm saying that's not efficient. Therefore, we have to find a step size for which our function is minimized. Okay. So therefore, what we do, we go to our previous formula phi of h, which is nothing but f function evaluated at x1, x0 plus h0 d. Okay. Then you evaluated phi h, which will be a function of h. Yes. And it's a function of only one variable. How you will find the optimum value? Take the differentiation, set it to 0. That's how you find the extremum, right? So h0 you find 0.2. Okay, once you find h0 equal to 0.2, you put it here, x1, and find the next iteration value. X1 you found. Now next what you will do? You find x2. Find x2. So next you find x2. Okay, find x2, which is x1 plus h1 d1. Okay. Here, next iteration, so on. If you do, you will slowly see that this quantity dk is less than epsilon. Okay. That means your value is getting converging to the minimum. Isn't it? See, if your value is converging means this quantity will be of similar value. That means h1 d1 should be closer to 0 or less than epsilon. H is a constant. So only way is the norm of dk should be less than epsilon. Okay. Now the next iterations we will do in Python. Okay. We will see how it approaches. This method, note that at every iteration we have to, at every iteration, like let me write, at every iteration, we have to update h, the step size, and also the phi of h. Okay. And it is not that easy to find h. We already know that by hand. It's getting complicated. Okay. So therefore, the question is, what happens if we take constant h? And what happens if we take find h like this at every iteration? Okay, that's our main aim. Okay, so let us move to Python. What's with you? Okay. So just go through this. Number of iterations, I'm taking 10,000. Okay. And this is my epsilon, 10 to the power minus 6. What is that epsilon? Norm of dk less than epsilon. That's the epsilon. Okay. For convergence, step size I already fixed, 0.01. Don't have to update again and again. What is my objective function? This is f of x comma y. You see lambda x I have defined. X is a vector. X of 0 means it's x. X of 1 means it's y. Okay. Check it is your same function. Okay. Now the gradient function, I gave Python what is the gradient function. It is just do the gradient and you will get this function. Okay. This is the gradient. I am iterating. X is your x naught minus 1 comma minus 1. This is your starting guess value. Starting guess. So now you have starting guess value. Now you have step size. Do you need any more information? No. You have everything. Direction also you have. I think direction we have to find. Direction we have to find. So for I in range max it like for 1 to 10,000, you run this iteration. Gradient equal to gradient function. Here you computed gradient. This is your direction. Okay. Like this linear algebra package you are taking, like lin alg dot norm. You are taking the norm of that gradient and you're checking if norm of that direction is less than epsilon, break. That means you already attained convergence. If you have not attained convergence, that means if b is not less than epsilon, then keep continuing iterating. Then what is that? X equals to x minus step size of gradient. Okay. I think you can take this. You can take a plus sign. I taught you using plus sign, right? X equal to xk plus 1 equal to xk plus hk dk. Here I have taken minus sign because you don't need to worry, because b equal to minus gradient you could have taken b equal to minus gradient, right? And the same thing, minus of gradient is same b. Are you getting? Okay. Okay. See, what I am saying is instead of this plus, what I have done here, I could have done better. Like my instead minus gradient, that is the direction. So it is just plus of that. I'm just writing b equals to minus of gradient. That's it. Nothing else. So here I am printing at every iteration, the iteration value, the x value, and my direction norm, my norm direction. This guy should be closer to 0 when we are approaching convergence. Okay. Then the minimum value I am evaluating at that value. At this value I am evaluating because this value is the value at which my function will be minimum. That's the hope, right? That's due to that hope we are iterating, right? Yes. So if you found out that x value using gradient descent, what you will do? To find the minimum, you evaluate the function at that value, x. So that's what we are doing here. Objective function x. So you're passing that x value to this. So it will evaluate here. So far clear? Hmm? Yes. Yeah. So that's it. So that's a very simple algorithm of gradient descent with just constant step size. Just constant step size. We are starting with the simplest case. Okay. So now you see how it is going. See these values, how many iterations it is taking. So you can see after 57 iterations, okay, and maybe still going, it just found 1.77, okay. No, sorry, not 57. We took 10,000 iteration, right? So where is that bar? And so it's still go like 10,000 iteration. Maybe the best I can do is run it again. Okay, done. Huh. So you see this, like at 2000 iteration only it converged. Okay. But it took a long step, right? Isn't it? 2000 iterations. It's too much. So that means it's not efficient. Okay. Taking constant step size is not efficient because it's taking 2000 iteration for just solving or finding a minimization function which you just computed in your notebook last week within 5 minutes. Okay. Just to half of your notebook using Sylvester criteria. Okay. So just taking constant step size, even though it looks interesting to take, and so we can't take. Not optimized. Okay, so after 2000 iteration, you can see this is our the norm of the direction. This is the norm of the direction, dk, which is b in the code. Okay, so this is less than epsilon. This is less than epsilon. Hence, we took, if it is less than epsilon, break. So it came out of the code. Okay, so you can see at 2 comma 1, at 2 comma 1, x equal to 2, y equal to 1, we are getting the minimum value -2 around. At this x and y value, we are getting the minimum location. Okay. All right. So next move towards another code. All right. Yes. Wait. So what we understood is taking constant step size is not optimizing because it's taking lot of iterations. We saw 2000 iteration for just solving that f value. Okay. And updating h value at every step is also computationally expensive. Okay. So therefore, can we be in the middle? Can we be in the middle? We don't have to take constant step size. We don't have to take updating step size at every iteration. Can we do something better apart from these two? So this is where Armijo, the scientist, came up with an algorithm, Armijo's condition. Okay, so what he said, instead of fully minimizing phi h, how about we partially minimize phi h? What we mean by partially minimize? That you know. Okay, that's what Armijo condition is. So then you will see, I will show you here. This is the Armijo condition, and how many iteration does it take? Yes, within 44 iterations. If you take Armijo condition, if you implement Armijo condition, which is not intuitive, it's not at all intuitive, I understand. It will not come to your mind, but that's the power of the scientist. Like, he will think something which no one thinks. So he found that, how about I partially minimize phi of h? Okay. Using that condition, you can see instead of 2000 iteration, it is just taking 44 iterations. You can appreciate. Okay. Next, maybe I will talk about this. There is something better also. Yes, this is also a better algorithm. In another algorithm, you are reaching at 35 iterations. Okay. So obviously this one will win. All right, this one will win. So intuitively, you might think, let us take constant step size and do. But it will be taking too much time. Okay. At every step, let us find the extremum value of phi h. That will also take too much time. But if you partially minimize the Armijo condition, using Armijo condition, it drastically reduces the step size by taking just 44 iterations. And we'll see, if you apply Newton method, better Newton method, it converges to 35 steps. So the method we are going to learn now, these two will be the efficient ones. Okay. And we will not go into derivations. I'll not go into derivation. I'll just say what I mean. But it will be understood just by applying common sense. So let us go to that condition first. Yes, we covered this one, right? We will cover this later. And also one more thing by this I forgot to tell you about is, suppose this is your function, okay? Let me tell you now, record it. And I should have covered this before I forgot. Anyway, so check the Armijo condition is satisfied. Okay, what is that Armijo condition? This is the Armijo condition, which is a bit different from your previous one. You will have an additional term of this. You will have an additional term this. Okay, not intuitive, I know, but it is there. So how shall we proceed with the method? Check the Armijo condition is satisfied or not. Check the inequality less than satisfied or not. If it is satisfied, carry on with the iteration. Okay. If it is not satisfied, then they are saying that decrease the step size. How you will decrease the step size? Therefore, you have a parameter tau, which is in between 0 and 1. Take 0.3. Previously it was h. Now it will be 0.3 h. So it decreased, right? So tau is saying between 0 to 1, and tau h is indirectly saying that decrease the step size, nothing else, by a factor tau. Okay, decrease the step size. Then third, what will do? Once you decrease the step size, check again, check Armijo condition satisfied or not. If not, decrease again h, decrease again h. There will be a h, decreasing, 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 so on. There will be an h for which Armijo condition will be satisfied. Okay, it's mathematically proved. Okay, and then you will continue that same iteration process and get to the minimum. And we don't know why, but this is a very not intuitive algorithm, but it converges very fast. This I thought to tell you. This is not gradient descent. This is gradient descent with Armijo condition. If you want to do gradient descent, you can do very easily, but it will take you 2000 steps, just fixed step size. Okay. But if you put Armijo condition in your gradient descent algorithm, it drastically gets fast. Instead of 200 iteration, it takes only 40 iterations. So let's go to our Python code. Okay. So yeah. Yes. This is the yeah. So what we are doing here? So what we are doing here is this is the line search algorithm. Don't worry about it. This function fx1, the objective function, and this is x minus step size into gradient. Fine. It's just the gradient. Fine. This is the quantity which you wrote in your notebook, check it, that x of k plus f of x of k plus beta into h dk gradient, check that. Is it the same formula for that? Is it? Hmm? Yes. Isn't it? Beta into h into gradient. Isn't it? So I'm checking the condition here. If fx2 minus fx1 is less than that, okay. So here I'm just checking the Armijo condition, okay. And if it is not satisfied, you decrease that step size. You can see step size equal to tau into step size, isn't it? Tau is in between 0 to 1. I have taken 0.5, okay. So same way, if you continue your iteration, this see, after that return step size, whatever is there, it is from the previous code. Whatever is there, it's from the previous code, isn't it? All we are checking, b is less than epsilon, everything is from the previous code. Okay. The only new thing we added is the Armijo condition. In the first half, this is where we have added the Armijo condition. This is where we have added the Armijo condition, and the rest part of the code is exactly the same as the previous one with constant step size. Okay. So we took the same code but applied the Armijo condition. With only the Armijo, see that very nicely very nicely it is getting converged. We started from here, okay, and it takes only 44 iterations. How it is going? I'll explain you. Mouse is very sensitive. Finally. So here is the starting point. Next iteration, it is going here. Next iteration here, here, so on. It's going to 2, 1. Can you check x equals to 2, y equals to 1? Isn't it the same location where you are experiencing the minimum of the function? One of the beautiful things for this gradient descent is, I would ask you, is do you observe anything from this diagram? Any observation from this diagram? It's a very nice observation. See, the direction to every iteration is perpendicular. This direction was the previous one. This is the new one. See the direction perpendicular. This is the previous one. This is the current one now. See the perpendicular. Every iteration you take is perpendicular except the first one. This is actually not a good thing. Like you will see, if you go deep into the method, you will see if you have this kind of perpendicular thing, it's not that good. Rather, this should not be like that. It should be going randomly. If he wants to find like optimizing the function in a, like finding the minimum of the function, it should not go in that way always. Okay. It can be some random motion. Anyway, so this is how it works. Okay. Same thing I am showing you here. You see this, how it reaches here. Okay. So this is one of the function plot. Okay. So you can see, we saw that if you increase the value of the function, f of xy equals to constant, the more constant, the more wider it spreads like this, isn't it? So you can see 0 here, 6, 8, 10, 12, the more width it is showing, isn't it? Is it okay with you? This is just the function plot. You just did FGH. No? You just did FGH using Desmos. I am doing more than that. I am doing 10, 20 iterations. So here I am showing I started from here, and you see how fast it is going till here. With just 40 iteration, it finds the minimum value here. The minimum value here is that 2, 1 or 2, something. So yeah, these are like this you can appreciate maybe. So this is how the iteration, I tracked that iteration. Anyway, so what you concluded from this? Time is it?